All right, these next three examples are a little more involved, and I'm going to have to show you sort of a technique for dealing with these. So this first one says the set of ordered triples x, y, z where x and z are equal. You could probably go through and figure out what this looks like if you thought about it for a while, but we're going to do this one algebraically. Here's what you do. Now I didn't leave a whole lot of space here, so I'm gonna make this big and then I'm gonna write small. So the way you do this is first let's check vector addition. The way you check to see if it's closed under vector addition is you pick two arbitrary vectors in the set and add them. Then you see, and then check whether the sum is still in the set. And now arbitrary here, it doesn't mean you just pick a random vector in the set. It means you pick a vector that you pick when you say arbitrary, what it means is it's going to have variables in it, something that could represent any vector in there. So for instance, I'm going to call the x coordinate A, I'm going to call the x coordinate A, the y coordinate B, and the z coordinate is supposed to be the same as the x coordinate, so that's going to be A as well. Then I'm going to pick another arbitrary vector. Let's see, I used A and B there. I'll use C and D here. Actually, no, I don't want to use C because we use that with the coefficient sometimes. So A and B, then let's use P and Q. This is P, this is Q, and this is P again because the X and the Z are the same. Now, when we add these together, up top we get A plus P. Here we get B plus Q. Down here we get A plus P. So when we do that, these two are equal. And that's what we were looking for. The X and the Z component had to be equal to each other. They're equal. Therefore, three little dots for therefore, this is closed under vector addition. All right, so we're halfway there. Now we need to check and see, is it closed under scalar multiplication? And so to do that, what we do is we pick an arbitrary vector in the set. So I'm going to call that ABA again, and an arbitrary scalar C. Now I'm going to take this and multiply it out. Let me come back up here. An arbitrary vector, I'm going to call it little v, and an arbitrary scalar C. And then we check to see if CV is in the set. So if we take this and multiply it out, you get CA, CB, and then CA again. So we check, is this in the set? Well, really we're asking, does it have the right form? Are the X and Z components equal to each other? And they are. So therefore this is closed under scalar multiplication. So we've got the two things we need, so therefore this is a vector space. So it seems like a lot of work, and I guess it kind of is, but that's what you need to do on something like this. Okay, let's look at example 308. I want to do this the same way we just did the previous example, but after that, this one is geometrically pretty easy to do, but I want to do it so that we practice using this technique. Set of ordered pairs x, y that have y equal 4. So for vector addition, let's see, what I'm going to want to do here is pick two vectors that have this form. And I'm not going to write all that down this time. I'm just going to write them out. Something that has an A and a 4 there. Something that has an arbitrary number there and a 4 there. So these two guys are arbitrary. Arbitrary vectors that have the right form. When you add them together, though, the top is A plus B, which that's fine, but the bottom is 8. So does this have the right form, namely that y is equal to 4? No. So not 4, therefore it's not closed. And really, if our only desire here was to say, is this a vector space or not, we could stop at this point and say, no, it's not a vector space. But I want to check scalar multiplication as well, just as practice. So pick an arbitrary vector with an A there and a 4 there, and multiply it by an arbitrary scalar. Words escape me sometimes. Arbitrary vector in the set. Now when we multiply this out, we get CA on top, and we get 4C on bottom. So now we have to ask the question, is this equal to 4? And the answer is, well, only if the only if the scalar we chose was equal to 1. So it doesn't work for all. It doesn't work for all scalars C. So it's not closed under scalar multiplication. And either one of those alone is enough to tell us that this is not a vector space. Now, it turns out there are actually two other ways we could see that it's not a vector space. One is the fact that it doesn't contain 0 vector. It only contains vectors that have something there and a 4 on the bottom. So we could also say it does not contain, let's scribble this out for the moment. There. Yeah, scribble that out for the moment. And this thing, it does not contain the 0 vector. That's enough right there to tell you it's not a vector space. And also, we can think of it geometrically. This is the x and y axis. This consists only of the vectors whose y coordinate is 4. So if you draw this in as a bunch of little arrows, it's all these little guys. And if you look at those, if you scale those by any amount other than 1, you're going to go off the line. So it's not closed under scalar multiplication. That's essentially the same thing that we showed up here, but up here we just did it a little more formally. And also, if you take any one of these guys, pick it up, and then add it onto another one, you're going to wind up with something that's no longer on the line. In fact, the coordinate of this is going to be 8, the y-coordinate. So writing it out like this is really just a more formal way of talking about what's going on down here. All right, let's do this example that I unceremoniously scribbled out. I'm going to copy that and paste it in below. All right, so example 309. And we'll ignore the stuff written above it there. The set of 2 by 2 matrices that have this form. All right, I want to do this 2 different ways. This is a 2 by 2 matrix, so we can't really graph it. But one thing to notice, there's no way this can have the 0 vector. The reason is, vectors that look like this, like if A is 7, then this down here is going to be 8. So that's one matrix in this set. If you put a 0 in for A, you get a 1 there. And if you put a -1 in for A, that's what you'd have to do in order to get a 0 there. So one way we could answer this is just saying, do these form a vector space? No, they don't contain the 0 vector. Or maybe I should say, it doesn't contain the 0 vector. Or I'll just write this. The 0 vector here is not included. Now, if we wanted to do this more formally, what we could do is we could pick 2 arbitrary matrices. One would look like this. And then when we add another one onto it, when you add these up, let's see, this becomes A plus B. This is 0, this is 0. And this down here becomes A plus B plus 2. Now the form that we're looking for here is that this entry is 1 more than this entry. And that's not the case on this guy. Because down here, this entry is 2 more than that entry. So that right there, we can look at that and say it's not closed under vector addition. And if you wanted to check scalar multiplication, if you did that first, that would also work. If you take the matrix A plus 1, 0, 0, if you multiply that by an arbitrary scalar, you get CA, 0, 0. Down here you get CA plus C. So does this have the right form? You're asking, is this equal to 1 plus that? And the answer is only if C is 1. So it doesn't work for all values of C. So it's not closed under scalar multiplication. All right, and I think that's our last example. I just want to say one more quick thing. The thing that messes you up on these, the things that make it not a vector space, are, in this case, the 1 messed things up. Notice the zeros, they didn't cause any problem. It's the 1. Up here on this problem, it's the 4 that messed things up. The thing that what messes things up is what I call a naked non-zero number. That's nice and alliterative. The naked non-zero number is the thing that makes things no longer be a vector space. If those had been zeros instead of a 4 there, it would have been fine. If this had been A plus 0, that would have been fine. But it's the, and what do I mean by a naked non-zero number? I mean it doesn't have a coefficient with it. I'm going to leave you with this example. This video is getting way too long, but I want to do one more thing. if you have something like this where you've got A, B, C, and then this one over here is 2A plus B, matrices of this form, this would be fine because there's no naked non-zero number. If you took two of these and added them together, what makes this of special form is that this entry is double this one plus that one. You don't have a non-zero number here that doesn't have a variable on it. So when I say naked, I mean a number like this, 1, with no variable on it. This right here, if you worked it out, would be fine. I'm not going to do it, but these would form a vector space. All right, and we'll stop there.